Before we trace data through this network, let's meet the hardware. Four pieces do all the work: the terminal at your home, the satellite overhead, the gateway on the ground, and the modem inside the dish. Here's what's inside each. Start with the terminal, the dish outside your home. It's a flat, phased array panel of hundreds of elements steered by a beamforming network that sets the face of each one. Behind it sit the RF transceiver and the modem that turns packets into a waveform. A small receiver gives it position and time, a motorized mount handles coarse aiming, and a single cable carries data and power down to your indoor router. Inside that dish is the modem, the digital brain. Packets arrive from your network, the link control sublayer wraps them, and the scheduler fits them into its granted slots. The physical layer turns them into a modulated signal, and the front end and the RF stage push it out to the antenna, and the reverse path brings the signals back in. Running alongside is a timing rail, a position fix, and a model of satellites track that lets the modem compute exactly when to transmit and how to pre-shift frequency for Doppler. Up in the orbit, the satellite is the other end. It carries three kinds of link: a phased array facing the terminals, optical laser terminals that mesh it to its neighbors, and a feeder link down to the ground gateways. An onboard router switches traffic between them, and underneath sits the spacecraft bus: power, propulsion, altitude control, thermal, and telemetry, keeping the payload alive and pointed. On the ground, the gateway is where the network meets the internet. Several tracking antennas plus a hard spare all feed one commodity network switch. A liveness heartbeat tells the switch which antennas have a live satellite, so it only routes down working paths. From there, traffic passes into the provider's point of presence and out to the global internet, while a management terminal handles the gateway's own bring up. Put them together, and the path is simple. Your terminal talks to a satellite, the satellite relays across its mesh and down to a gateway, and the gateway hands off to the internet. Then the reply comes back the same way. Four pieces, one connection. But none of this carries a single byte until a terminal comes online. First, it must listen and log to the signal, align its timing, claim an address, pull its configuration, and register with the network. Only then is it allowed to transmit. That handshake, provisioning, is where the story really begins. A brand new terminal powers on. An out-of-band activation has already bound it to a service profile. But over the air, it's a stranger with no assignment. Here's the catch: it needs a grant to transmit, yet it has none. Before it can be scheduled, it must break in. The terminal has no idea where in the sky its satellite is, and its own antenna's orientation is unknown. So a phased array steers its beam across candidate direction, and at each one also sweeps the operating frequency, listening for a serving beam's downlink. When energy with the right structure appears, it locks onto the direction and channel as its entry point. Each frame opens with a known sync sequence. Correlating against it produces a sharp peak that pins down frame timing and the carrier frequency offset, the Doppler of a fast-moving beam. Now the terminal knows when the downlink frames begin. From the channel estimation symbols and pilots, the terminal estimates the downlink and equalizes it, enough to cleanly demodulate the beam. But for its own first burst, it has no uplink feedback yet. So it transmits at a deliberately conservative fixed MCS. Link adaptation only tunes the rate later, once the terminal is in the loop. It still has no grant, so its very first uplink burst goes on a shared random access opportunity. If two terminals pick the same slot, they collide. Each backs off a random amount and retries until one gets through cleanly. The burst must arrive inside a narrow target window at the beam. Rather than probe and correct step by step, the terminal computes its send ahead from its own position and the beam's ephemeris. So the first burst lands close. A small measured residual is trimmed until it locks. This is the single terminal seed of many terminal convergence the uplink uses every frame. With a clean burst received, the network assigns a link layer identity, authenticates the terminal, hands it its uplink and downlink channels and its starting MCS, applies the service profile, and places it in a scheduling group. It now is admitted. Admitted, the terminal finally appears in the map and receives grants like everyone else. Cold start is a one-terminal closed loop. From here on, it is the many-terminal scheduled world of uplink and downlink schedulers every interval. Every interval, a fresh uplink frame opens. Many ground terminals have data waiting, but they are half duplex. The channel is narrow and they would collide. So the scheduler hands out grants. First, how many bits ride each symbol? Each terminal reports a smoothed signal-to-noise ratio and, separately, its error rate. Clean signal but high errors mean interference, so the rate drops anyway. Bits per symbol then sizes every grant. A round-robin sweep picks the terminals that have data to send. For each, buffered bits divided by bits per symbol gives its symbol requirement. A terminal with nothing queued still earns a small floor grant, so it can ask again next time, not go silent. Those requirements are sorted into bins, measured against the minimum grant. 0, below 1 unit, 1 to 2, and 2 or more. The scheduler then allocates from the smallest needs upward, which keeps a few hungry terminals from starving the many small ones. Now, the packing. Pulled lowest needs first, terminals are grouped into a burst, and a burst is capped at 4. That cap is deliberate. It keeps the per burst arithmetic cheap. Each burst claims a slab of the frame's frequency by time grid, and once 4 are placed, the next terminals open a fresh burst. Here is the key idea. For each burst, the scheduler totals the payload symbols its terminals need, converts that into resource blocks, and finds the required burst length, trimming any unused tail. Then it subtracts what burst spent from the frame's running symbol budget and repeats form, size, subtract until the budget runs out and the frame is full. Every grant becomes one row in the uplink map. Which frequencies, which symbols, which burst. The map is broadcast down to the group, and each terminal reads only its own row, then transmits up into that slot. Many senders, one packed frame. The uplink scheduler is the bursty one. 4 per burst, idle terminals flowed. It sets where each sits. One layer sets when each fires. Sending up is the hard direction. Many ground terminals must share a single satellite receiver, and they sit at very different distances, so their signals take different times to arrive. Left uncoordinated, those signals collide. The fix splits across two isolated modules. An RF, or the air interface side, that times every transmission so bursts arrive together, and a phi side that packs them into an orthogonal grid that receiver separates once scheduler has handed out the slots. A far terminal signal travels farther than a near one's. If every terminal simply transmits at the same moment, their bursts reach the satellite at different times and overlap. Interference and collisions happen. Distance alone breaks a shared uplink. So the satellite acts as a scheduler. In its downlink, it broadcasts a map of grants. Each terminal is told exactly which slice of time and frequency it may use. A terminal transmits only inside its grant. Request, get granted, and then send. A shared receiver only works if bursts from different distances land at the same instant. So each terminal sends early by exactly its own travel time. The far terminal fires first, the near ones later, and all bursts converge at the satellite at one target time, co-timed and not smeared. Each terminal computes its own send-ahead from physics. Its GPS position plus satellite's own orbital track gives the exact distance, hence the propagation time. From that, it derives when to fire, and because the satellite is racing across the sky, it also pre-shifts its frequency to cancel the Doppler effect before transmitting. Now, the waveform itself. Those granted co-timed bursts tile a time times frequency grid. With OFDMA, each terminal is assigned its own non-overlapping resource blocks. Because the blocks are orthogonal, many terminals transmit in parallel in the very same frame and the satellite separates them cleanly. Each terminal's burst opens with a known unique word so the satellite can find it and lock timing. Then channel estimation symbols let it measure the channel. After that come the payload resource blocks, sprinkled with pilots to track drift around an empty DC tone at band center. One receiver, many distant senders. The scheduler grants each a slot. The RF side has every terminal, send ahead, and pre-compute Doppler, so bursts arrive together. The phi side tiles them into an orthogonal grid and shapes each burst so it can be found and measured. Ground to space, perfectly interleaved. Every interval, the satellite broadcasts one frame for many terminals. No burst to coordinate, a wide channel. So far, more terminals fit per frame. The scheduler decides each one's slice. Like the uplink, each terminal reports a smoothed signal-to-noise ratio and, separately, its error rate. High errors at clean signal mean interference, so rate drops. Bits per symbol sizes each grant, and terminals of similar rate pack together well. The scheduler walks the terminal's service flow queue round robin, picking only the non-empty terminal and flow pairs. A terminal with an empty buffer has nothing to send, so on the downlink it's simply ignored. No slot is reserved for it, it just doesn't appear. The selected flows are sorted into bins against the minimum grant. Below 1 unit, 1 to 2, 2 or more. As on the uplink, the scheduler allocates from the smallest needs upward, keeping a few hungry terminals from crowding out the many small ones. Here is a real difference from the uplink. The downlink has no bursts. It's a single broadcast frame. So terminals with like modulation are simply tiled in together, no per burst grouping. And before any grant is sized, the frame's header symbols are subtracted off the top, leaving the usable symbol budget for the payload. Here's the main idea. The budget is split across flows. Each grant fills whole code words, and the leftover sliver, smaller than one code word, can't be used alone. So rather than waste it, the scheduler carries that residual forward to the next flow, which gets its share plus the remainder. Flow by flow, the budget ticks down until the frame is full. Every grant becomes a row in the downlink map. Which frequencies, which symbols. The whole frame is broadcast to the group, and each terminal reads only its own row to pull out its data. The idle terminal's rows simply stays empty. The downlink scheduler is the broadcast sibling. No bursts, a wider channel, idle terminals ignored, not flowed, same front end, it sets where each one's data sits. A satellite in low orbit moves fast and sits hundreds of kilometers up, yet must deliver internet to many users at once. We'll trace it the way a terminal is actually built. Two isolated modules. First, the PHY, an efficient multi-carrier waveform, a repeating frame the receiver locks onto, and a constellation that adapts to link quality. Then the RF front end, an electronically steered beam that carries the physical frame down. Start in baseband. The data writes OFDM. The wide channel is divided into 1,000-odd orthogonal subcarriers, each a slow, narrow tone. A short, cyclic prefix guard in front of every symbol absorbs echoes so they don't smear into the next one. Robust delivery with no fragile single carrier modem. Symbols are grouped into a repeating frame. It opens with known synchronization sequences the receiver already knows. Matching against them reveals exactly where the frame starts and lets it measure timing, channel, and Doppler shift from the moving satellite. Then come the data symbols, a closing marker, and a guard gap. The last phi job is choosing the constellation. The modem watches each link's signal-to-noise ratio and adapts the constellation. Strong link, pack more bits per symbol. Weak link or rain fade, fall back to a rugged choice that survives noise. Throughput is constantly traded for reliability as conditions change. Now the waveform leaves baseband for the RF front-end. The antenna is a flat-faced array, hundreds of tiny elements, no moving dish. By applying a sloped phase shift across the elements, their waveforms add up in one chosen direction. Tilt the phase ramp and the beam steers electronically, instantly toward a spot on the ground. One satellite paints several narrow spot beams at once, each lighting a different ground cell. Because the beams are tight, the same frequencies can be reused in cells that are far enough apart without interfering, multiplying total capacity. Beams hop between cells to share time where demand is high. The satellite races across the sky in minutes, so its beam continuously re-steers to hold the cell. As it nears the horizon, a make-before-break handover passes the cell to the next satellite climbing into the view, so the stream to the ground never drops. Two clean modules. The PHY carries data on orthogonal subcarriers, wraps it in a sync-led frame, and adapts the constellation to the link. The RF front-end then steers a beam with phase, reuses spectrum across spot beams, and hands off before the satellite sets. Space to ground, hundreds of kilometers in millisecond. Internet data arrives from the network as plain packets. Before it can write the radio, something has to package it, protect it, and decide how hard to fight for reliability. On a long link, that job earns its own layer. Distance changes everything. A lost packet can only be noticed and resent after a full round trip. And over the link, that's a long wait. Worse, to even allow a resend, the sender must hold a copy of every packet until it's confirmed. Do that for every flow, the memory cost explodes. So the link control sublayer runs a small assembly line. A data unit is queued per service flow, packed to fit the size of the grant the scheduler handed out, and fragmented if it is too big. It's stamped with a header and a checksum, so the far end can catch errors, then aggregated and passed down to the radio. The same sublayer offers three behaviors: transparent, pass through untouched, unacknowledged, package the data, but if a piece is lost, let it go, and acknowledged, track every piece and resend anything that doesn't arrive. More reliability costs more buffering and more delay. Reliable delivery runs a sliding window. The sender transmits packets and keeps a copy of each one in flight. The receiver reassembles them in order and sends back acknowledgments. When there's a gap, it returns a negative acknowledgement. The sender retransmits the missing piece from its buffer, guaranteed in-order delivery or a lossy link. Here is the key idea. The sublayer watches the link quality and switches modes on the fly. When the link is clean, it runs unacknowledged. No buffering, minimal delay. When quality drops past a threshold, it switches that flow to acknowledged mode and pays for reliability. When the link recovers, it drops back to the cheap mode again. And it makes that choice per flow, not for the whole link. A latency-sensitive video call can run unacknowledged, while a file transfer runs fully acknowledged, side by side through the same radio, each getting exactly the guarantee it needs. Take the packets from the network, encapsulate them to fit the radio's grants, choose speed or certainty, adapt that choice to the live link, and decide it independently for every flow. One sublayer tuned to the cost of the distance. This is where the satellite network meets the rest of the internet. A provider connects through big tracking antennas that feed a network switch. The whole challenge, keeping that pipe up while satellites race past. Each satellite is overhead for only a few minutes. As it sets toward the horizon, the antenna locked onto it loses the link and has to slew across the sky to find the next one rising. During that swing, a single antenna is down, a gap no serious service can accept. So the gateway runs several antennas, all feeding one switch. Their satellites set and rise at different moments. So while one antenna is slewing, the others still hold live links. The switch's only job: send traffic down a path that's currently alive. It learns which paths are alive with a fast heartbeat, a continuous liveness check between the switch and each antenna. If a path stops answering, the switch notices within milliseconds and stops routing to it, then resumes the moment it returns. This is ordinary off-the-shelf machinery. Now, the clever part. The cable from antenna to switch is always fine. What actually fails is the satellite link far above it. So each antenna deliberately flips its own heartbeat to down when its satellite sets, even though the wire is healthy. A commodity switch, believing that the path is dead, reroutes around it automatically, no custom coordination software required. Watch the rollover. Antenna A's satellite sets, its heartbeat goes down, The switch instantly shifts traffic to B and C. A is loose, finds a rising satellite, comes back to life, and rejoins. Then B does the same, covered by the others. Because the sets and rises are staggered, at least one path is always live, and the backhaul stays up the entire time. For extra margin, keep one antenna as a hot spare, idle but ready. If any active antenna falters, the spare takes over its role instantly, and the spare duty rotates to share the wear. Commodity parts and a standard heartbeat, adding up to a link that almost never blinks. Point many antennas at the mesh, feed them into one switch, run a heartbeat that reports the satellite link's health, let the switch route around anything that sets, and keep a spare in reserve. An always-on bridge from orbit to the internet. Click a link at home, and the answer can come back through outer space in a fraction of a second. Let's follow one packet through every stage we have built, from your room to the internet and all the way back. Hop 1. Up to the satellite. Your device hands the packet to the dish. The link control sublayer wraps it. The scheduler grants it a slice of the grid, and the dish sends ahead so its burst lands exactly on time. In a single beamed burst, your request is in orbit. Hop 2. Across the laser mesh. The satellite rarely talks straight to your destination. Instead, it relays the packet satellite to satellite over inter-satellite laser links, routing across the constellation toward a satellite hovering over a distant gateway. Hop 3. Down to the ground. Over that gateway, the satellite forms a steered downlink beam, the same framed, error-protected waveform that serves homes, and delivers the packet to a big ground antenna, space to ground in milliseconds. Hop 4. Through the gateway edge. The antenna feeds a network switch that always keeps a live path open as antennas hand off and their satellites set. From the switch, the packet enters the provider's point of presence. And now, on to the ordinary internet, to the destination server. Then the reply makes the whole trip in the reverse. Gateway, mesh, satellite, your dish. Because these satellites orbit low, the entire round trip takes only tens of milliseconds. Far enough away to touch space, close enough to feel instant. Now, look again at that laser mesh. Today it routes packets, but those same satellites carry processors, and those same links could just as easily move a machine learning model's data instead of web traffic. The relay constellation becomes a distributed computer and its inter-satellite links a training fabric in orbit. Up through a synchronized burst, across over a laser mesh, down on a steered beam, through an always-on gateway, out to the internet and back in tens of milliseconds. 5 layers, one path, and the same fabric that carries your click may one day carry computation itself.